Yo people, what's going on? Welcome to Vedantu JEE English. My name is Pahul. If I am audible and visible, please write here in the chat box. You know the drill, yes? So people, today we are going to do alkyl halides and reaction mechanisms, the theory of which we had discussed in our previous session that was on Friday, right? So on Friday we had discussed SN1, SN2, E1, E2, E1, CB reactions, and today we are going to use that knowledge quite a lot and think about this as a continuation of that lecture that we had on Friday. We have a bunch of questions for you today, and along with these questions, whatever concepts are there, we're going to revise those concepts as well. Alrighty, let's do this question. This is a JEE Main 2023 question, and I'm surprised to see this kind of a question come in JEE Main, honestly, because such questions of such thorough depth, I would expect these to be in JEE Advanced, but surprisingly they've asked about this in JEE Main. So let's try to do this, okay? So what's going on over here? There are two reactions that are given. Now on first glance, they look very similar to each other. Can you see? There is a benzyl chloride which is substituted with OCH3. There's another benzyl chloride which is substituted with a nitro group. Now in both cases we are reacting these with a nucleophile, and in both cases the chlorine is getting replaced with the nucleophile. Pretty similar. But now the question asks you, what is the order of the first reaction and what is the order of the second reaction? Nice. This particular question requires a lot of depth of understanding of SN1 and SN2, E1, E2, E1, CB reactions. First of all, now how to solve this? Let's go step by step. First of all, when you look at the question, you realize that this is an organic chemistry question, and then you see order of the reaction. In the entirety of your syllabus of organic chemistry, where have you seen order of the reaction? You've seen order of reaction in either SN1 or SN2 or E1, E2, E1, CB, etc. Now obviously these two are substitution reactions. So the question is definitely asking you about either SN1 or SN2, at least that much is clear, right? Now the next step is to understand the difference between these two substituents and how they would reveal the information of whether the reaction is an SN1 reaction or SN2 reaction. First of all, let's look at the nitro group. The nitro group, as everyone knows, is an electron withdrawing group. Yes, this is a very good -M group, one of the strongest out there. So it withdraws electrons from the system. Now, my dear friends, let's discuss a little bit about what's going on in an SN2 reaction. Let's say we have any substrate, okay? We have any substrate, chlorine over here, and we want to do an SN2 reaction with this particular substrate. So what's going to happen is a nucleophile is going to approach this carbon from the backhand side, right? Now, if, listen to me carefully, the first step, the only step of this reaction involves this and this reacting together at the same time. If this carbon has a positive character on it, the oxygen will be attracted to it even better. Isn't it so? If this already has a positive character on it, the oxygen will be attracted to it very nicely. So how do I increase the positive character on this particular carbon? Obviously, I can introduce an electron withdrawing group. Withdraw electrons, the carbon gets a positive character. It becomes much more attractive for the OH negative. Yes, one more interesting thing which we had sort of discussed in the Friday's lecture. What does the transition state look like? The transition state looks something like this. This is the carbon. The bond with chlorine is being broken. Just a second. The bond with oxygen is getting formed. Yeah, right? And I had told you that at this point of time, you can imagine that this carbon has a p orbital which is interacting with both OH and chlorine at the same time. Yeah, this is a very simple p orbital that's interacting both with chlorine and OH at the same time. So if you provide resonance to this particular p orbital, it's really nice. That's why our benzyl structures are really good for SN2 reactions. And also realize electrons of OH are also interacting over here and electrons of chlorine are also over here. Can you see there are a lot of electrons involved in this particular process? The electrons that are coming in from OH are also involved. The electrons that are going away with chlorine are also involved over here. This particular system right now is quite electron rich. So if you take away a little bit of that electron burden from it, it will become stabler. So what you can do to stabilize the transition state a little bit further is introduce an electron withdrawing group over here. So the crux of the entire matter is that SN2 reactions are favored by electron withdrawing groups. Alright, SN2 reactions are favored by electron withdrawing groups. Now over here, since both these substrates are benzyl compounds, right? Benzyl chloride, benzyl chloride. Benzyl, as I told you in the previous class on Friday, are good for both SN1 and SN2. Over here, just because you have an electron withdrawing group, this particular substrate would favor an SN2 reaction mechanism. Do you remember the rate equation for the SN2 reaction mechanism? The rate equation is equal to K times the alkyl halide and the nucleophile that is attacking. The rate depends on both the alkyl halide and the nucleophile at the same time. And what's the order now? Since the powers of both of these are 1, order is 1 plus 1, that is 2. This part is fine. Now let's talk about the first case. In the first case, you have an electron releasing group. Let's think about the SN1 reaction mechanism once again. In the SN1 reaction mechanism, I'm sure you realize that once you get rid of the leaving group, you form a carbocation. And obviously, to stabilize a carbocation, what do? You release electrons into it. Electron releasing group or electron donating group. So it's going to give some electrons to the carbocation. The already positive thingy is going to get some electrons and feel a little more stable. So pretty obvious that electron donating groups will stabilize an SN1 reaction's reactive intermediate. And therefore, in the first case, you have an SN1 reaction. What's the rate law for the SN1 reaction? Do you remember that? Rate law is K times just the alkyl halide. Since it's a unimolecular reaction, there's only one molecule that's breaking apart into the carbocation. Nothing is attacking it. So the nucleophile strength doesn't matter over here. How the nucleophile gets attracted to this doesn't matter. Carbocation is getting formed, that will attract the nucleophile later. So over here, electron donating groups will stabilize the intermediate, and the rate law depends only on the alkyl halide, only on the substrate. The power over here is 1, and therefore the order is equal to 1. Right? So what's the correct answer out of all of these? Option number A. Reaction 1 is of the first order and the reaction 2 is of the second order. To the untrained eye, to the people who do not understand SN1 and SN2 reactions in depth, most likely you would have done the question incorrectly. But for those of you who now understand the exact dynamics of SN1 and SN2, this is an easy question. Nice, right? So people, that's the beauty of this question. I'm surprised to see this in JEE Main, honestly, because such questions are usually asked in JEE Advanced. Great. Cool. Account is saying, what if NO2 was present in the meta position? Then its electron withdrawing effect would not be as strong, because then the electron withdrawing effect would be limited to just the inductive effect. And then this particular substrate can choose to go either from SN1 or SN2 mechanism, both. And in the laboratory, if you do that, if the nitro group was in the meta position, both the mechanisms would sort of compete with each other. Okay. So generally when SN1 and SN2 both can happen and both are competing with each other and both are giving you the same product, the faster reaction mechanism is the SN2 reaction, because it's a single step mechanism. So just because of the speed of things, SN2 is slightly more than SN1. But both of them compete at the same time in the case that you've asked. Alright, great. So people, just to remind you guys once again, I'm sure our other teachers have also told you about these things, that we have a free test series, All India test series available for you, courtesy of Vedantu. So what you can do to enroll into this test series absolutely for free is go and check out the link in the description box. There is something called V-Quiz as well, Vedantu Daily Practice Problems, which means that you get tests, questions, everything that you need to gear up for your JEE preparation, all for free. Links in the description box down below. So check it out in case you want. Fine? Badhiya. Now let's do this question. This is a standard, this is just an okayish question. There's nothing difficult about this question. Compound from the following that will not produce precipitate on reaction with AgNO3 is. Let me tell you the simple reaction that we are talking about. Whenever you have an alkyl halide, especially when the halide is a chloride, bromide or iodide, alright? When you react it with silver nitrate, what happens is that you form a carbocation and it is stabilized by the nitro group for some time, for the time being. Yeah, for time being it is stabilized by the nitro group's negative charge, but this can then further react. At the same time, what's formed at the side is this silver halide. You will have either silver chloride or silver bromide or silver iodide. Now the fun thing about silver halides is that these are not very soluble in nature. These don't get dissolved in solvents easily. So what happens is they will simply precipitate. And since they precipitate out, what are you doing? You are taking away the product from a reaction mixture. When you take away a product from the reaction mixture, do you remember Le Chatelet's principle? Naumida ma'am must have taught you about it. Yes? So if you take away the product from the reaction mixture, the entire reaction will get driven forward. So that's why this is a very special reaction used to generate carbocations. And then you can do whatever you want with the carbocations. So now, in the first case, what kind of a carbocation are we forming? If I remove the bromine, I form a very nice allyl carbocation. Can you see this carbocation is in resonance with the double bond and the benzene ring? Nice resonance stabilized carbocation can be formed. Okay, fine. Second case also, this is a benzyl carbocation, very stable. We all know about it. Look at the fourth case first. We'll come to the answer later. This is the answer obviously. Let's look at this case. Over here, if you remove the bromine, the carbocation is formed over here. Okay, still possible. Do you realize the difference between these two? This is the one that we discussed in the class last week. On Tuesday in GOC's class, we had discussed a lot about this particular carbocation, cyclopropyl carbocation, really stable. This one is different. Yeah. You don't have that extra carbon over here. You simply have the carbocation in the ring itself. This is still fine. It's not really bad. In fact, it's a good carbocation. Do you realize that this particular species what is this species? Do you realize that this particular carbocation is aromatic in nature? Yeah. 4n plus 2 electrons in cyclic conjugation. Look at the p orbital picture over here. This is one p orbital, this is another p orbital, and this is a vacant p orbital of the positive charge. All three are parallel to each other. And what is the number of electrons being delocalized in the system? 2 electrons. So 4n plus 2, you have to put n equal to 0. Aromatic system essentially. Yeah? Or you can think about odd number of electron pairs in conjugation. So there's just one electron pair in conjugation, therefore it's aromatic. Yeah. So this can also get formed very easily. So A, C and D, these can be formed very easily. By the way, this is option A, this is option C, this is option D. Maybe that wasn't so visible. This is option B. If you thought this is option C, then okay, fine, not a problem. But now I'm telling you. So if you remove the bromine from here, you are forming a carbocation on top of a double bond. What is this case? This is the case of a vinyl carbocation, which I told you is not going to get formed at all. This carbon was already sp2. Now you take away electrons from it, it has to become an sp carbon. An sp carbon has to be Straight, linear, right? Not possible. Yeah, this has to have an angle in it. Just doesn't work out. Okay, this is an unstable carbocation. The molecular orbital diagrams of this do not work out properly. It has very unstable energy. So just keep it in your mind that vinyl carbocations or phenyl carbocations not going to get formed. Hence the answer to this question is option number B. Let's not spend more time over here. Let's go to the next question. This is a question that I do not like. Sorry. This is a question that I do not really appreciate because this is a reaction the reaction's mechanism itself is not sure. Even till this date, scientists don't really know what's the exact mechanism behind this particular reaction. Okay, fine. So, can anyone tell me what this reaction is called? So what you have over here is an alkane. Yes. What you have in the question is a straightforward alkane. No alkene, no alkyne, just an alkane. And in the alkane, you are putting anhydrous AlCl3 in the presence of HCl and heating it up. What's going to happen? Do you have any idea? Hemashri is saying, can we write the examination without good preparation of second year organic chemistry? If you're talking about 12th class organic chemistry, then it's very difficult to perform well in organic chemistry without the knowledge of 12th class organic. So it's better you practice some of it at least. Okay. Sorry. Random bro is asking, if both electron withdrawing group and releasing groups are present in a ring, then what happens in electrophilic aromatic substitution? You draw the resonating hybrid, see where the negative charges are sitting, and that's where the reaction will happen. As simple as that. So what is this reaction? My dear friends, this is a reaction that's given in NCERT in the chapter of hydrocarbons. Hydrocarbons, NCERT. Okay, and this reaction is known as the reaction of isomerization. Very weird reaction, to be very honest with you. It's a weird reaction. And as I told you, the reaction mechanism of this particular thing is not really certain. It's sort of an uncertain reaction mechanism. I will tell you whatever knowledge I have. Take it with a pinch of salt. Do not try to remember that mechanism. No one's going to ask you about the mechanism. The end point of it all will be clear to you in the next 5 minutes. But just for fun, just so that it's easy for you to remember these things, I'll give you a glimpse of the reaction mechanism, the possible reaction mechanism. So this is a 6 carbon species, 1 plus 4 plus 1. So 6 carbons, there we go. Now what we are doing is we are reacting it with AlCl3 in the presence of HCl. AlCl3 is anhydrous at the moment. Can you think about its chemical properties? This is what the structure is going to look like. Trigonal planar. And if you notice carefully, you'll realize that this has an incomplete octet. Yeah? The aluminium over here has an incomplete octet. So to complete its octet, it's going to want some more electrons. And therefore, this type of a species would act as a very good Lewis acid. What do we mean by a Lewis acid? Lewis acids are species that would happily accept electron pairs. So what this tries to do is, from this HCl, H positive, Cl negative, the chlorine gets attracted towards this aluminium. And ultimately, you form something like this. Can you tell me the shape of this molecule? It's going to be tetrahedral. So this tetrahedral molecule has a negative charge on it. Obviously, you've given it a negative charge. And on the side, you have this H positive. Now comes the weird part. Now comes the very weird, the very not so good part about this particular reaction. Now what happens is this H positive has nowhere to go. See, you have anhydrous systems over here, right? Anhydrous means there's no water. If there was water, then this H positive could have gotten into water, get solvated, exist very happily over there. But there's no water over here for this H positive to react. So this becomes quite a reactive proton. And what this proton tries to do is it tries to approach this particular alkane that we have. This alkane, what it does is very peculiar. What it can do is it can take one of its hydrogens over here. This H positive can capture this hydrogen with the electrons. These electrons in the bond, they can go with this particular hydrogen. H positive, H negative combined together go away. Okay? H positive and H negative combined together, they go away, and what you are left with is a very weird carbocation. And this carbocation is obviously not happy because the solvent that you are using over here is there's no water. Water can stabilize the carbocation easily, but there's no water over here to stabilize it. So this is an unstable carbocation. And being an unstable carbocation, it can rearrange in a very random fashion. Carbocation rearrangement, I'm sure you remember it. In carbocation rearrangement, you do a hydride shift. If the hydride shift is not possible, then you do a methyl shift. But over here in this particular possible reaction mechanism, what is proposed is that this can undergo lots of weird shifts. One of the shifts can be this particular CH3 that is here, this entire bond can move over here. And what you will get is something like this. So this intermediate that we form is susceptible to a lot of rearrangements. And because of these rearrangements, you get this as a product. This is what? This is an isomer of the original compound. This is what? This is just a chain isomer of the original compound. So that's why this reaction is known as an isomerization reaction. And what happens in this reaction is that the system gets rearranged into something else. You just do a little bit of rearrangement, form something else. That is all that's going to happen. Okay. So this is the broad idea of the proposed reaction mechanism for this particular equation. Now, is anyone going to ask you about this reaction mechanism? No. No one cares because nobody knows for sure what the exact reaction mechanism is. Therefore, whatever I told you is just for your own understanding. You don't need to remember it. What you need to remember is if you see this alkane plus Lewis acid, all you have to do is rearrange the entire thing. Do not introduce any new chlorines. Okay. Random, bro, that's what I said. This reaction mechanism is just a proposed reaction mechanism. No one knows for sure exactly what's going on over there. People just know the starting point, the ending point, and then someone proposed this reaction mechanism. The only, the only reason why we even think about it is that there's no water, so things are extremely reactive, and there's a lot of heat that's given in this reaction. So then we can expect unexpected things to happen, if that makes any sense. So don't introduce any chlorines, don't form rings and all. Just take one thing, put it in a different position. That's all. So I agree, this is not a very this is not a standard reaction, but surprisingly it's given in the NCERT. Therefore, so now if it comes in your examination, I'm sure you'll be able to choose the correct answer out of the options. They will give you simple options in such questions, by the way. They won't give you complicated options. They will give you simple options which you can easily decipher. Great. Let's move on to the next question now. There we go. The major product formed in the Friedel-Crafts acylation of chlorobenzene is. This question came in JEE with options, of course. but I haven't written any options over it because I wanted to revise this entire reaction with you guys. So, now, do you guys remember what this reaction mechanism is? Do you guys remember the reagents for it? What we are doing over here is chlorobenzene's Friedel-Crafts acylation. What's chlorobenzene? Let's draw that. Pretty simple. There we go. Chlorobenzene. And in Friedel-Crafts acylation, what we have is a Lewis acid, as always. And at the same time, you have something that can turn into an electrophile. Friedel-Crafts acylation is an electrophilic aromatic substitution reaction. Electrophilic aromatic substitution. Okay. Now, what is acyl group? Acyl groups are these. When you associate this group to something, let's say you put this on benzene, whatever, this is your acyl group. So what you have to do is somehow introduce an acyl group towards this particular starting material. Now, how do we form this electrophile? How do I form that particular substituent? You start with acetic acid. CH3, C double bond O, single bond OH. This is acetic acid. Now to acetic acid, if you add a chloride ion providing reagent, you can give it PCl5, you can give it SOCl2. And once you do that and provide the reaction some energy, the OH group over here is replaced by a chlorine. Let's do that. CH3, C double bond O, single bond Cl. This particular compound is known as acyl chloride. Acyl group with a chloride. So you take the acyl chloride over here. Yeah. CH3, CO, Cl. As usual, what's going to happen is there's no water present. So the AlCl3 would want to attract the chlorine towards itself, like we did in the previous question. So the chlorine gets attracted towards the aluminium, and what you are left with is an electrophile. As soon as the chlorine gets attracted over here, this electrophile can go and approach the benzene to do a reaction. What does the electrophile look like? Technically speaking, it looks something like this. But it's not possible to isolate this electrophile. As soon as it gets formed, it goes and reacts over here. Fine. So now this electrophile is going to react with benzene. Which position will it react is the next concept that we're going to discuss. Do you guys remember the electrophilic aromatic substitution reaction, or should I revise the mechanism for you? Tell me in the chat box, please. If you want me to revise the reaction mechanism, I shall do so. But you can tell me. Sorry. There has to be a CH3 over here. My bad. Thanks for correcting me, Arijit. Cool. We'll revise the electrophilic aromatic substitution mechanism as well. Chalo. Let's do that revision now. So, take a benzene ring. It's a very simple reaction mechanism. And you react it with an electrophile. Electrophile is something that wants electrons. So, electrophiles on their own are positively charged or positively charactered species, right? Take one of these pi bonds of benzene, polarize them in any direction, right? And then this particular carbon will approach the electrophile, and what you form over here is our reactive intermediate. We haven't touched these double bonds at all. We've polarized the double bond towards the right hand side. So the left hand side carbon, this one at the top, will have a positive charge now. therefore a reaction intermediate, reactive intermediate. On this carbon, there's already a proton. Do you realize? All these carbons have 1 hydrogen on them. So there's already a hydrogen over there. And now another bond is getting formed with the electrophile. Yes. This is our reactive intermediate. This is also known as the arenium ion. In chemistry, whenever we say anything ium ion, it means a positive charge. Bromonium ion has bromine positive. Oxonium ion has oxygen positive. Lithium ion has lithium positive. Well, lithium's name is lithium, but you get the point, right? So arenium ion means arene is an aromatic species, but you've taken away the aromaticity, you've turned it into an ium ion. So this is called an arenium ion. Anyway, this is obviously the slow step of the reaction, rate determining step, because you're forming an unstable species over here. Now what you have to do is simply lose the proton from here. What you can do? Let the proton go away. How will this proton go away? Do you remember we had a Cl negative? We had this, right? Such a species can capture the proton. Don't worry about it. So you remove the proton from here. Sorry, I have put the arrows in the wrong direction. You remove the proton and give the electrons to this carbon. So H positive leaves, and what you are left behind with is C negative. That negative can combine with this positive charge and form the double bond once again. And now instead of this hydrogen, you have the electrophile substituted onto the benzene ring. So what you've done over here is simply remove the proton. Very nice. Now a few interesting things about electrophilic aromatic substitution. First case, what if I put an electron releasing group on top of the benzene ring? People, let's make some resonating structures. One of the most enjoyable things to do is making resonating structures because it's a lot of fun. So let's make the resonating structures of OCH3. Let's take the lone pair of oxygen out of the two. Let's take one lone pair of oxygen, put it towards this side, and let's polarize this particular pi bond towards the right. So the resonating structure that we can make after this one looks something like this, wherein you'll have a double bond OCH3 at the top. This oxygen now has a positive character, obviously. There is a negative charge that comes on this particular carbon. Double bond, double bond. Fine. Now, my dear friends, the next resonating structure could be, we just push this further. Here, very quickly, I'll draw the remaining resonating structures. I hope you are also drawing these with me. Please don't sit idle. Yeah. So the double bond comes here, the negative charge comes here. Perfect. One more. Double bond OCH3, positive charge. Cool. This is what's going on. And you take it further from here. It's fine. These are the resonating structures, and now let's try to make the resonating hybrid. Yeah. Remember we did a question about resonating hybrids in the GOC class last week. So once we make the hybrid, that's gonna look something like this. OCH3. There's gonna be a partial double bond over here on oxygen as well. The oxygen is gonna carry a partial positive character, and at the same time, you're gonna have a partial negative character on the ortho position, on the para position, and on the other ortho position as well. Can you see? Negative charge, so the average of all of these will be something like this. Negative character here, negative character here, negative character here. Fine. Now, if an electrophile were to approach this particular benzene, obviously the negative parts will get attracted to the electrophile. So either your ortho groups would react or your para position will react. Either the attack will happen from the ortho position or the para position. Therefore, if I put an electron releasing group on benzene, electron donating group on benzene, this will force the electrophile to either react at the ortho or the para position. So I call this ortho para directing. It directs the electrophile to go either at the ortho position or the para position, right? Now, one more thing. Electrophile is positively charged and you've given some extra negative character to the benzene ring. It's going to react faster, right? Compared to a regular benzene. In a regular old benzene, there is no charge. Just some electrons, but there is no charge, extra charge as such. Yeah. But over here, you are creating a little bit of an extra negative character on the benzene. So this extra negative character is going to help it react with a positive character or a positive charge. So this becomes more reactive than a usual benzene. That is why we call electron releasing groups activating in nature. For electrophilic aromatic substitution reactions, electron releasing groups activate the reaction. Now similarly, if you had an electron withdrawing group, forget about the resonating structures for a bit. If you had an electron withdrawing group over there, for instance, let's take a nitro group. So the nitro group will do resonance similarly, but it will create positive characters on the ortho and para position. So now if you force an electrophile to react with this, first of all, the electrophile would not want to react over here because there are positive characters now. But if you still force the electrophile to react with this benzene, the only possible place is meta position. Because why would a positive charge approach a positive character? No. So therefore, in the case of an electron withdrawing group, you deactivate the benzene because it's difficult to do the reaction now. You're reducing the reactivity. So you call it a deactivating system. And this is meta directing. Okay. Fine. Haritanam, in such cases, you can do nucleophilic substitution, but this is just electrophilic substitution for now. Cool. Alright. Now, the special case that we are talking about over here is of a chlorobenzene. Halogen substituted benzenes are a little weird. See, when we talk about halogens, I hope you remember this. If you don't, then now I'm going to revise it for you. Halogens have very good minus I effects compared to their mesomeric effects. Halogens are electron withdrawing in nature because of their high electronegativities. So their minus I groups are pretty strong. I mean, their minus I effects are pretty strong. But at the same time, these halogens have lone pairs, right? So one of those lone pairs can theoretically go and resonate with the entire system. But their mesomeric effect, their resonance effect is very subdued, very bad. Their inductive effect is stronger than their mesomeric effect. Why? Because in halogens, the orbital overlap between the p orbitals of halogen with the p orbitals of carbon is really bad because of the size difference. Orbitals need to be of similar sizes to do good overlap. But over here, size difference is there. Chlorine is huge, bromine is huge, iodine is huge. Yeah. So because of that high difference in size, the resonance between chlorine and carbon is bad. Their orbital can't overlap properly. So their mesomeric effect is poor. Their inductive effect is great. So because of their electron withdrawing inductive effect, these halogens are deactivating substituents. This has deactivated the benzene ring, perfect. But at the same time, there is some mesomeric effect as well, right? So because of this slight mesomeric effect, if you force an electrophile to react with this particular benzene, it will still go towards ortho-para position. So overall, you've taken away electrons from the benzene system and therefore it is deactivated for electrophilic aromatic substitution reactions. But still, if you force it, because of the slight mesomeric effect that is present, you still have the electrophile going towards the ortho or para positions. Right? Now, in this case, Friedel-Crafts acylation of chlorobenzene, what you have to do is simply associate the acyl group at the para position. Why not the ortho position? Because in the ortho position there will be a lot of steric hindrance. Chlorine has a lot of electron cloud, huge electron cloud. This entire thing is very bulky, so they'll keep repelling each other. Simply put it at the para position. So the product of this particular question is this. It was one of the 4 options given in the examination, but I took this question over here for you so that I could revise the entire mechanism as well. Now Random Bro, that's a name in the chat box, is asking, sir, can you please show electrophilic aromatic substitution with both electron releasing and electron withdrawing groups substituted in 1 and 3 positions? Interesting. So what this guy is asking us is sort of a borderline case, but let's try to do that. Does this scratch your itch, my friend? Does this scratch your itch? So let me make the nitro group in green color. So because of the nitro group, let's try to write the electronic effects that are going to happen. So for nitro, the ortho and para positions are going to have a positive character. And because of this guy, the ortho and para positions are going to have what? A negative character. Now what will happen to the reaction? Now where should I do the reaction? Because there is an activating thing that's going on and a deactivating thing that's going on. Can anyone suggest what will happen in such cases? See, in such cases, you cannot predict what's gonna happen. You cannot predict what's gonna happen. Because say, this is stronger than this. How will you decide whether this is a stronger electron withdrawing group than this is releasing? You have to do an experiment in the laboratory. That's the only way to go about it. To check what's going to happen over here, the only thing you have to do is go to the laboratory and check it out. Okay? You go to the laboratory and check it out. That's all. You can't do anything else about it. And depending on how the electrophile which attacks over here interacts with nitro group or OH group, if it can do hydrogen bonding with the OH group, maybe it gets associated over here. If it does hydrogen bonding with the nitro group, maybe it gets associated over here, etc., etc. So such cases cannot be predicted. Such cases you need to go to laboratory to understand it. Now, if say, both of these were nitro, then all of these positions that are marked are deactivated. So the only position remaining is this one. So such cases are easy to predict, but when you have such a case, you can't predict. You have to go to the laboratory to check it out. Fine. Nice. Let's go to this question. Simple. Extremely simple. Can you tell me the answer? This is a multiple correct. So multiple correct. So in JEE Mains, this question was given with more options at the end, saying only A is correct, B and C are correct, A, C, D is correct, something like this was given at the end, but you have to figure it out without those options over here. So first of all, we have the SN2 reaction mechanism. So in the SN2 reaction mechanism, what happens is You have a nucleophilic attack, and for the nucleophilic attack, you want less steric hindrance. Yes, we've discussed this quite a lot in detail in the last class that was on Friday. Yeah. The first substrate given over here is simply a 1 degree halide, and the substrate given over here is definitely a 3 degree halide. So comparing these two, obviously this is going to have more steric hindrance, this is going to have less steric hindrance. Yeah. So the first case is going to have a higher rate than the second case. This is correct. Nice. Let's look at option number B. In option B, you're talking about the SN1 reaction. So for SN1 reactions, we need more stable carbocations. In the first case, you have a benzyl carbocation that will get formed. Remove the bromine, positive charge over here, resonance stabilized, very happy. In the second case, you will form a simple 1 degree carbocation. Now this can rearrange and get converted into a benzyl carbocation, that's fine. But in the first step, in the immediate formation of the carbocation, this is better. This will become better later. So this will obviously be faster. That's what's given to us. That's faster than this. Great. Now electrophilic substitution. We've just revised the reaction mechanism. So in electrophilic substitutions, if we have electron withdrawing groups, that deactivates the system. First case only chlorobenzene, second case nitro substituted. Nitro is an electron withdrawing group, it will deactivate this benzene even further. This will give you a faster reaction, this will give you a slower reaction in terms of the electrophilic substitution. Yo, someone new, what's up? Please do watch the lecture later because the second last question that I will discuss, someone new, is ring expansion. And I know you've been asking for ring expansion for a really long time. Cool. Strong and capable, very nice, bro. Good stuff. So let's do the last option now. So you've got nucleophilic substitution. What do we mean by nucleophilic substitution? See, the reaction mechanisms of nucleophilic substitution are a little different from electrophilic substitution. The reaction mechanism of this, if you want me to revise, I will do it at the end of the class. Okay, it's a little weird. We'll do it at the end of the class, or I'll give you a link of the class where I've already done that reaction mechanism. But nucleophilic substitution means you are trying to approach the substrate with a negatively charged species. When will a negative species get attracted to benzene? When the benzene itself has positive character. Yeah. Negative species, nucleophiles are negative species, so negative species will get attracted to benzene if the benzene itself has positive character. How do you introduce positive character into the benzene? You put an electron withdrawing group. Yeah, so this electron withdrawing group will create these positive characters on ortho and para positions, and therefore this nucleophile will very easily be attracted to those positions or even this position, and bromine can go away as a leaving group. Yes, random bro, exactly. Meisenheimer intermediates and the benzene mechanism as well. We've done that in catalysis classes. I'll share the link with that of that class with you guys for those of you who want to study this reaction mechanism properly. But yeah, this question can be solved without the knowledge of the mechanism because it's very obvious that the nucleophile needs a positive character to get attracted. So obviously the right hand side system will be faster than the left hand side system. Therefore this option is also correct. All of these are correct. Someone new, yes, exactly. But yeah, this is also done. Let's go to the next question. This is one of the simplest questions that they could have asked. This is like, I mean, come on. Sorry. Been speaking for a really long time today, so my throat and nose have given up. Haritanam, obviously, man, the terms are, they sound fancy, of course. Rahul Rana, so the thing is that this particular channel takes classes only in English, but if you want to study the same things from me in Hindi, the channel Vedantu JEE is there for you. This is Vedantu JEE English. There's a channel called Vedantu JEE where I have done literally the same things today itself in a live session, which I took at 8 p.m. So yeah, over there I teach in English or Hindi, whatever. So maybe that channel is a little more relevant to you. So, this one. The pair from the following having both compounds with net non-zero dipole moment is. Omar Adnan, very nice. Let's do this simple question. Cis-butene versus trans-butene. What is cis-butene? This. What is trans-butene? This. If you look at the dipole moments, this guy is going to have two dipoles in these directions, and then both of them, these are vectors, right? So they'll give you a resultant vector in the upwards direction. So this will have a resultant vector. Over here, this vector and this vector will cancel each other out, opposite vectors. They will cancel each other out. So this has a dipole moment, this does not have a dipole moment. Trans is non-polar, cis is polar. Please remember that. So over here, trans-butene is, cis-butene has, trans-butene has zero dipole moment. We don't want that in the answer. Second case, I'm sure a lot of you have figured out already that that is the answer. Let's try to make the structures of both of those. The first case is CH2Cl2, carbon, let's make it like this, 2 chlorines and 2 hydrogens as well. So hydrogen carbon, if you want to think about the dipole moment, both of them will be towards carbon. Yeah, very slight small dipole moments. And at the same time, the chlorines, which are going to give it the real dipole moment, the significant dipole moment, one dipole in this direction, the other dipole in this direction, both of them are going to add together and give you a resultant vector over here. Yeah, both of them will add together, give you a resultant vector in this particular direction. So this has a non-zero dipole moment. The other structure that is given to us is chloroform. Yes, CCl3H or CHCl3. So chlorine, chlorine, or I will make it in this manner. Right? So this carbon has 3 chlorines like this. Look at the fingers. All 3 are sort of pointing in the downwards direction. So if you take a resultant vector, it will be in the downwards direction. So this particular compound also has a resultant vector of the dipole in the downwards direction. Both have non-zero dipoles, and therefore this is the correct answer. Over here in option C, benzene has zero dipole moment. Over here 1,4-dichlorobenzene has zero dipole moment. This is para-dichlorobenzene. So one chlorine on top, one at the bottom, they'll cancel each other's vectors out. Simple. Haritanam, I would love for you to do a Google search and check that out. Rahul has asked a very interesting question. I was waiting for someone to ask this. Rahul is saying, sir, how is the direction of the dipole moment defined? See, what is a dipole? A dipole is a certain pair of charges that is at a certain distance from each other because of an equilibrium. Yeah. So because of some established equilibrium, this positive and negative charge has a certain distance in them. Yeah. Now the magnitude of this particular dipole moment is decided by Q into D, where Q is the charge. You can take either the positive charge magnitude or the negative charge's magnitude. Okay? So this is the magnitude of either the positive charge or the negative charge, and D is basically the distance between them. This is the magnitude. Now the sign, it obviously either is in this direction or in this direction. Does not matter. In physics, we say that the dipole is in the positive direction. In chemistry, we say that the dipole is in the negative direction. Because it's a convention. We can choose. In physics, you choose to point this direction. In chemistry, you choose to point in this direction. Because at the end of the day, what you want to do is just add dipoles properly, right? So if all the vectors are towards positive charge, okay, fine. If all the vectors are towards negative charge, okay, still fine. You get the point. So you can choose the direction. In physics, we choose positive. In chemistry, we choose negative. That's just the convention that we follow. Cool. This question is done. Pretty simple, standard question. No complications. I mean, if you got this in your shift, consider yourself really fortunate. But then we have this question. So some students got that extremely simple dipole moment question, and some students got this one. This is a tricky question. All right. This question is a little tricky. Have a look at it, then I'll show you the options as well. Haritanam, yeah, man. Everything is convention. So, you have a starting material which has an olefinic double bond. Olefinic double bond means carbon-carbon double bond. And then you have an acidic group on the other side. And the reagents that you are using, first of all, you're using bromine, Br2, and then you're using sodium bicarbonate. What is this going on? What is this going on? To the people who understand the reaction mechanisms a little better, and for those of you who've practiced these reactions, I don't think this is a very difficult question. This is not a very difficult question. But those of you who haven't done enough practice in organic chemistry, this question will look tedious. See, the test for unsaturation in terms of double bonds or triple bonds is reaction with bromine water, and the test for acids is reaction with bicarbonates. So we are combining both of these things together and forming an organic product. Now the options that are given to you are quite interesting. Bromines added onto the double bond, nothing happens to the acid. Bromine added only on one side of the double bond, again nothing happens to the acid. Bromine on one side, nothing happens to the acid. And then this case where a bromine is also there and the acid has also transformed itself. Now let's say you do not know what to do in this question. A little bit of logic that could have helped you over here is, see, in the substrate, I've been given reagents. One part of the reagent reacts with this side, the other part of the reagent reacts with this side. So both the sides need to undergo a transformation. The olefinic double bond will react and the acid will also react. So both sides need to look different in the product. The only product with both the sides looking different is this one. That's the logic that could have helped you in the examination. Fine. But now let's think about how. How will this happen? And the more questions you practice for organic reactions, the better you will get at predicting these ideas. So the first thing that happens over here is that the bromine reacts with the double bond. Do you remember that reaction? If we have any double bonded system and we react it with bromine in the presence of a non-polar solvent like CCl4, the first thing that gets formed is a halonium ion intermediate. Do you remember this? The bromine essentially over here, Br, gets broken into Br positive, Br negative, and this positively charged bromine overlaps with the p orbitals of the pi bond, right? So this kind of an overlap happens where bromine approaches both the p orbitals. You can think about something like this. This is the p orbital, this is the p orbital, and this is bromine's orbital. So these three orbitals are overlapping each other at the same time. Fine. So that's the bromonium ion for you. It's a reactive intermediate. And then the bromonium ion gets approached by the Br negative, this Br negative, approaches from the opposite side. So one bromine comes from the top, the other comes from the bottom. It's an anti-addition reaction mechanism, right? Fine. Over here, what we'll do is, first of all, we'll make the bromonium ion. Let's make the reactive intermediate first. Double bond O. And this is where your bromonium ion will get formed. Perfect. Now comes the role of this NaHCO3, the sodium bicarbonate. People, do you remember that experiment that your science teacher must have given you in childhood? That go home, take some baking soda, that's what sodium bicarbonate is, react it with some acid. They would probably tell you to react it with lemon juice, yeah, lime juice or lemon juice. And then what happens is it starts to bubble, suddenly you have homemade soda. Yeah, remember that? So this is a typical reaction wherein an acid reacts with sodium bicarbonate, acid-base reaction. Effervescence of CO2 will happen over here. Yeah. So this entire thing gives CO2 plus hydrogen gas is also released because yeah. And what do you have at the side? What remains? Na positive. Yes. Sorry, what am I doing? Why am I removing H2? H2, one OH and this H get combined together to form H2. I am sorry for writing hydrogen. So yeah, you have Na positive. So what will happen to that Na positive? That will sit with this O negative. Right? This O negative will sit with that Na positive. CO2 will go away, water will be water. Fine. Now, this O negative is going to compete with this Br negative for the further reaction. If the solution is present inside your house, why would you go outside finding a solution? Intramolecular reactions are relatively easier than something approaching from the outside. So when this and this compete to react with the bromonium ion that's formed, this one takes precedence, reacts faster, okay? And therefore, what you form at the end is a cyclic product. How to form the ring? Just do a little bit of numbering. Numbering will help you recognize the correct ring. 1, 2, 3, 4, 5. You can do numbering however you want. No need to worry about it. So obviously we're forming a 1, 2, 3, 4, 5 membered ring. Let's make the 5 membered ring over here. This is the 5 membered ring. Let's number it. 1, 2, 3, 4, 5. Okay. So on carbon number 1, it's not a carbon, it's an oxygen. Remove this and put an oxygen over here. Great. On carbon 2, there's a double bond O. Fine. On 3, 4, nothing. 5, this is where the reaction happened. And on 5, there's another carbon called carbon number 6, which is not a part of the ring. And then on carbon 6, you will have the bromine. Yeah? This bromine will basically move like this. So on carbon number 6, you will have a bromine. This is your final product. Nice. Coolio. So when we look at the options, this is the correct answer. Random bro, see the thing is I will do that when we are closer to the JEE advanced examination. Right now we are targeting only the JEE main examination. So the questions are going to be more main relevant than advanced relevant. Uchiha, it does. Sodium bicarbonate happily reacts with COOH groups. It does not react with OH groups, but it does react with COOH groups. Okay. Cool. Rahul is saying how to study for physics board from scratch. I mean, I would suggest just study the NCERT of physics. That will help you a lot in board examinations. Cool. let's do the next question. Very simple once again. Correct order of reactivity for haloarenes towards nucleophilic substitution. They're just asking about the reactivity. They're not asking about the reaction mechanism over here. So for reactivity, again, what you have to do is nucleophile will approach, negative charge will approach, which means you have to have a positively charactered benzene. Just chlorobenzene, fine. Over here, you have a very nice electron donating group. This has 3 times nitro, nitro, nitro electron withdrawing groups. This has just 1 electron withdrawing group. Yeah. So, over here, more electron withdrawing groups implies more positive character to the benzene, implies better attack of the nucleophile onto the benzene. So, obviously over here, D is going to have the highest rate, then you're going to have B, then A, then C. Simple. Very simple. Okay? So this was one of the options. Great. Let's move on to the next question. Nice one. So what's asked over here is, choose the halogen which is most reactive towards SN1 in the given compound. So hear me out. These are not the final options of the question. You basically have to choose A versus B in all of these. And then you have to come up with A, B, B, A, whatever. And that was given as options. Okay. So whatever you come up with over here was given as, 4 options, and you had to choose the correct option. So essentially what you need to do right now is choose out of bromine A and bromine B, which one is more reactive towards SN1. Out of iodine A, iodine B, which one is more reactive? A, B, which one is more reactive? A, B, which one is more reactive? So, SN1 means carbocation stability. Benzyl carbocation, very nice. Some 2 degree carbocation, not as nice as benzyl. Yeah, this can rearrange later, but we don't want to think about later. Immediately, this is better. So, A is better in the first case. Second case, if I form a carbocation by removing the iodine, allyl carbocation, resonance stabilized. If I make a carbocation by removing this iodine, 1 degree carbocation, no resonance. It can rearrange to form a resonance stabilized carbocation, but that will happen later. Immediately, this is the most stable carbocation. Therefore, A is better in this case as well. In the third case, you have a bridgehead carbocation. Yeah. In the third case, you have a bridgehead carbocation. What do we mean by a bridgehead carbocation? Let me tell you. If you have a leaving group over here, let's say, and you remove it to form a carbocation over here, this will never happen. That kind of a carbocation is never formed. Why so? Because carbocations are sp2 carbons. Yes. sp2 carbons with a vacant p orbital. Now sp2 carbons have to be planar in nature, trigonal planar system, yeah? Trigonal planar system. Can this particular side ever be planar? If you try to flatten this out, yeah? If you try to flatten this angle, this angle, this angle all have to be squashed to 90 degrees. Isn't it? Nice, beautiful angles. You have to flatten them down to 90 degrees. You are introducing an extreme amount of angular strain. Because of that extreme angular strain from 3 different sides, this carbocation is not possible. Bridgehead carbocations cannot be formed. This is also known as the Brett's rule. Some scientist called Brett, I don't know the exact name of his. This guy told us that bridgehead carbocations cannot be formed. So it's called the Brett's rule. Anyway, this means that you can't form a carbocation from this particular bromine. This one is pretty simple. You remove it, you form a nice 3 degree carbocation over here. It's not a bridgehead. Bridgehead is where all these rings are coinciding. This is the bridgehead. If you think of this particular carbon chain as a bridge between the existing ring, then this can be called a bridgehead. This vertex is not a bridgehead. You can remove the bromine, put a positive charge over here, that will be a 3-degree carbocation, very happy. B is better. Last one, extremely simple, 3-degree carbocation versus 1-degree carbocation, so obviously A will be better. So out of the options that were given to you in the examination, you had to choose the one that said AA, BA, CB and DA. Cool. Om Dutt, cool man. I hope you're having fun scouting around. Let's go to the next question now. Okay, let's do this. Can anyone tell me what's the name of this particular reaction? What's the name of the reaction? It's a named reaction, it's a very common reaction. And for those of you who remember the name, very good. So this is an I negative, by the way, and this is a Br negative. Just a misprint that the negative charges are missing. Very nice. Good job, Umar Adnan, Haritanam, Arthur, Dinesh, Random Bro, Soumya. Very good job. This is known as the Finkelstein reaction. And this reaction is nothing but a simple iodide exchange reaction. Why is this reaction necessary? Let me try to explain that part to you first. How we generally synthesize alkyl halides or haloalkanes is that we start with some alkane and we try to react it with some halogen in the presence of UV light. In the presence of UV light. This is your typical free radical halogenation, the very first reaction of alkyl halides chapter. Now in free radical halogenation, chlorine and bromine give you the reaction. Okay, chlorine and bromine will be able to give you the reaction very easily. In case of fluorine, this reaction is not possible. It's very difficult to do the reaction in case of fluorine, and if you forcibly do it, providing it a lot of energy, it's an explosive reaction. Everything starts to explode if you give it enough energy to happen. So fluorine's reaction with alkanes, we would not do that unless you want to blow things up. When we come to iodine, the reaction of iodine in the presence of light is very slow. Okay, the free radical halogenation with iodine is extremely slow. So slow that it can take days for the product to get formed, and it's also a reversible reaction. Slow reversible reaction, we do not want to mess with this. So what we can form are products like this, which is either a chloride or a bromide, and then we can use the Finkelstein reaction to replace the chlorine or bromine with iodine to finally get an alkyl iodide. So creating an alkyl iodide directly is not possible, therefore we use such iodine exchange method reactions. Fine. Now how this reaction works is extremely simple. Extremely simple. You have some bromide or chloride, you react it with Ki. This I negative can do a simple backside attack, quintessential SN2 reaction. Quintessential means typical. So there's a typical SN2 reaction that happens over here. Backside attack of iodine. Instead of the bromine, you now have iodine, and at the side you have KBr. The interesting thing is that acetone selectively dissolves I negative. I negative is easily soluble in acetone, but Br negative, Cl negative, F negative, that's not soluble in acetone. Okay, this is not soluble in acetone, and therefore what happens is KBr is precipitated out. If you take the product out of the reaction mixture, the reaction is driven forward. Le Chatelier's principle once again. So the solvent that we choose over here is very smart. Iodine is soluble in the solvent, so it participates in the reaction very nicely. But when bromine is formed, Br negative, it just precipitates. So it does not participate in the reaction anymore. It does not do a reverse reaction anymore. Perfect. Now let's look at the options. The solvent used in the reaction solvates the ions formed in the rate determining step. I taught you about solvation when we were doing the GOC's previous year question class. In the question where we were discussing the basic character of amines. Remember that question? We were discussing basic strength of methylamines. So I taught you about solvation as well. So the thing is that solvation happens only in polar protic solvents. Water, being a highly polar molecule, can do solvation. But acetone over here is an aprotic solvent. Aprotic solvents do not do solvation like water or protic solvents can do. Therefore, solvation is, you don't even have to consider it. Fine. Then Br negative can act as a competing nucleophile. No, you've taken it out of the reaction mixture. Precipitated. Perfect. The reaction can occur in acetic acid also. No. Because acetic acid is a protic solvent. Acetic acid is more polar. High polarity, it can also dissolve KBr. It can also dissolve KCl. So the precipitation which drives this reaction will not happen in acetic acid. No, this reaction can't occur there. Obviously, the last statement is true. Let's read it and understand what the statement means. The transition state formed in the above reaction is less polar than the localized ion. What do we mean by the localized ion? Localized ion means just a simple anion like Ki. I negative is a simple anion. It has a full negative charge on top of it. Compare this I negative, which is the localized anion, to the transition state. What does the transition state look like? The transition state looks something like this. SN2's transition state. We've revised this really well in the Friday's lecture and even in a few questions that we did today. So over here, what's going on is there is a partial negative character here. There is a partial negative character here. And some of the burden of these two is shared by the carbon. The p orbital of carbon shares the burden of these negative charges. So this is not as polar as a singular anion with a full-blown negative charge on top of it. Yeah, this is less polar. That's what's given in the option number D. This is true for all SN2 reactions, by the way. The SN2 reactions, the transition state is less polar than the individual anion. Nice. Good question, right? Badhiya. So, one assignment for you, the class is not over yet, we have a couple of more questions to do. One assignment for you that comes into my mind after teaching you about this question is, please also study about or revise the Schwarz reaction. Okay, please also revise and study the Schwarz reaction. JICHU is asking, sir, is this a previous year question session? Yes, it is. Cool. So the Schwarz reaction is essentially a fluoride exchange reaction. So that is used to create fluorides out of chlorides, bromides. Fine. So just take a look at that reaction as well. Chalo ji. For those of you who are still watching, very nice. This is a beautiful question. This is from those days when JEE Advanced used to be a subjective examination. When step marking, writing questions, writing the answers properly in the answer sheet was a thing from 2001. Nice. So what we'll discuss in this question is something really interesting. Let's try to read the question, understand what it asks us about, and then finally there's a very interesting concept that we will discuss and revise through this question. Cyclobutyl bromide, let's make that. On treatment with magnesium and dry ether, forms an organometallic compound A. We all know what that is. Let's just do that reaction. Magnesium in the presence of dry ether. Grignard reagent formation. Yeah. So we are forming the Grignard reagent over here, and we'll simply have MgBr fine. So we formed the Grignard reagent, very nice. We do it in dry conditions, because if dry conditions are not there, then what will happen? Can anyone tell me? If you have even a little bit of water over here, then what will get formed? Can you tell me in the chat box? Let's read the rest of the question. The organometallic reacts with ethanol to give an alcohol B after mild acidification. Let's try to do that reaction. So this is reacted with ethanol. Ethanol, also known as acetaldehyde. Omar, Random Bro and Haritanam, very nice. So if you have even a trace of water over here, what's going to happen is, see, this particular system, the carbon is partially positive in nature, the bromine is partially negative in nature. Yes, because bromine's electronegativity is higher. Now that you've made this organometallic reagent, since alkaline earth metals electronegativity is very less, this will have the positive character. The carbon over here will have a negative character. Yeah. Cool. This will have a negative character. Now, my dear friends, what can happen is if you introduce water into the system, this bond is very fragile, by the way. This bond can easily be broken. Lots of electronegativity difference. So, when this bond gets broken, if you have H positive, which is there in an acid or it's there in water as well, the H positive will directly react with this carbon negative and a CH bond will get formed, an alkane will get formed. That's why we avoid water, we use dry conditions. Ether is what? Something like this, diethyl ether. Oxygen, yeah, whatever. Chalo, let's do this reaction now. So first of all, we will react both of these in dry conditions because we don't want the alkane to get formed, right? So once we do this reaction in dry conditions, what's going to happen? The negatively charactered carbon will attack over here. The pi bond of oxygen will get polarized towards oxygen, and then the O negative can get stabilized by the MgBr. Let's make that product. This is what's going on. A new bond is formed over here, which I have made in green color, and then that is associated with this particular carbon. I'll mark that in blue. This carbon already has a CH3 on it. Let's make that CH3. Now this has an O negative on it as well. And this O negative for the time being is satisfied by the MgBr positive. Now once you do the slight acidification of this, after this product is formed, then you do the slight acidification. Where is it? Yeah, there you go. Mild acidification. So now you reacted with H positive and then the MgBr goes away and you form an OH over here, right? So this is alcohol B. Great. So we've written the structure of A and we've written the structure of B. Now, this alcohol reacts with an equivalent amount of HBr. This reacts with HBr, and it's given that the product formed is really peculiar. The product formed over here is 1-bromo, 1-methyl cyclopentane. This is the product. Okay? What just happened over here? How did we go from a cyclobutane to a cyclopentane. Lakshmi, this is ethanol, not ethanol. Ethanol. AM भाई, ये वेदांतु जे इंग्लिश नाम का चैनल है, एक और चैनल है हमारा जिसपे वेदांतु जेई नाम है उस चैनल का, जहाँ पे हिंदी में ही पढ़ाता हूँ मैं। तो ये सारे क्वेश्चन जो भी करा रहा हूँ ना अंग्रेजी में, ये आज ही मैं हिंदी में पढ़ा के हटा हूँ। तो भाई वो चैनल पे जाके क्लास देख लियो मेरी। ठीक है। So the interesting thing that's happening over here is known as ring expansion. Nice. Ring expansion. So let's try to do that now. One part of the question is over. The other part, this explain how C is obtained from B. This carried the most marks. When you were writing this in the subjective type answer sheet, you had to actually explain this step by step carefully. Step marking. So let's do that now. Let's try to form this compound starting from this particular alcohol. Yeah. I have created a little more space on the next page for the same. Let's use that space. So we start with our weird alcohol that we've created. Yeah. This is the alcohol. And we are reacting it with HBr. Whenever we have alcohols in acidic media, the first thing that happens is protonation of the alcohol. After the protonation happens, what will we have? We'll have an OH2 positive over here, just like we used to do in dehydration of alcohols. And then this OH2 can leave away. OH2 is what? Water. So this is a very good leaving group. So if you remove the water molecule, what you are left with is a very interesting carbocation. Now this carbocation can undergo ring expansion. So what we need to do from here now is do ring expansion. See, what happens is, whenever you have small rings, like a 4-membered ring or a 5-membered ring, these rings have a lot of angular strain in them. Yes, the angle over here is supposed to be 109.5 degrees because of the tetrahedral carbon, but right now it's close to 90 degrees, right? So it wants to get rid of that angular strain, and therefore it would like to take any opportunity to expand the ring if possible. This ring expansion happens in 4-membered rings, 5-membered rings, they can form 6-membered rings. In some cases, there is ring contraction as well. In some cases, 7-membered rings can get turned into 6-membered rings also. That is a very rare case. No one will ask you that in the examination. So now we have to do ring expansion. One word of caution. Cyclopropyl carbocations do not undergo ring expansion. Okay, sorry, not this one. This one. Yeah, cyclopropyl carbocations do not undergo ring expansion. Let's not worry about those. These are already pretty stable. I have told you this does not have a lot of ring strain because the bonds are weird. We have discussed this in the GOC session last week. Anyway, so now how do we do the ring expansion? Essentially, we will first of all number the carbon atoms. Number the carbon atoms properly. Let's call this carbocation carbon atom 1. This is 2, this is 3, this is 4, and this is 5. Alright. Now in ring expansion, what will happen is this carbon number 5 will break this bond towards itself. The single bond that's there between 2 and 5, you break it towards 5, and then you move this bond towards the positive charge. Alright? Move towards 5 and then it goes towards 1. So the electrons are taken away from 2, given to carbon number 1. So carbon number 2 will now get a positive charge and a bond will be formed between carbon 1 and 5. Cool. Now this doesn't happen in 2 steps like I've shown over here. That's not how it happens. It happens very rapidly. So we do not draw these 2 separate arrows when we are showing ring expansion. We simply draw this kind of an arrow. Got it? That this entire bond breaks towards carbon number 1. So finally what we will form is a 5-membered ring. Yeah, because now 5 and 1 are connected to each other. So we make a nice 5-membered ring. We number the carbon atoms. Let's call this 1, this is 2, this is 3, this is 4, this is 5. 1 and 5 are bonded now, very nice. Obviously carbon 2 will have the positive character because you've taken away its bond. So positive charge comes on carbon number 2. And carbon 1, this one, already has a methyl group. There's a CH3 on it. So let's just put it over here. This is what happens after ring expansion. Now, this Br negative that's been sitting on the side waiting for the reaction to happen. Do you realize if it reacts here, we still don't get the product? If this bromine reacts in the place of the carbocation we have, it will form 1-bromo 2-methyl cyclopentane. But this is 1-bromo 1-methyl cyclopentane. Now what do I do? Yeah. So the carbocations jumping around is not over yet. What happens now is your typical carbocation rearrangement. We all know that there is a hydride ion as well on this particular carbon. We haven't drawn the hydrogen on the carbons because it's a bond line formula. But this carbon has a hydrogen, and that hydrogen can go through a typical hydride shift. 1, 2 hydride shift. Yes. And once that happens, the final thing that will get formed is this particular carbocation. This guy can react with the bromine and you will have the final product. 1-bromo 1-methyl cyclopentane. So in the JEE Advanced back in 2001, you had to not only draw this entire thing, you had to explain at each step what's going on. You had to explain the ring expansion. Not in a lot of detail, but at least in some detail. So after a ring expansion, one rearrangement is still possible. Alright. After the ring expansion, one rearrangement is still possible. Cool. So this was one of the most entertaining questions that I had for you today. And the interesting thing is, after solving such questions, JEE Main's questions will look very easy to you, isn't it? So that's why I always suggest you guys to solve JEE Advanced questions as well. JEE Advanced previous year questions are gold. Make sure you practice them. Perfect. Now people, just the last two questions that I'm going to show you, you will solve them on your own. I don't know why they asked this in the examination. What do they expect out of you? I have no idea. I hope such a question does not turn up in your examination, but let's see. In the following halogenated organic compounds, the one with the maximum number of chlorine atoms in the structure is. Why? Who's going to remember all of these structures? I have no idea. But they sort of expect you to. I mean, come on. So, if I were to encounter this question in my examination, I would straight away leave it. I do not want to risk negative marking. I would leave this question. I won't even think about it. If you want, these are the structures, okay? This is what chloral looks like. This is what gammaxene looks like. This is what chloropicrin looks like. This is what freon looks like. So, the answer over here is gammaxene. But yeah, man. Why would they ask this question? I've got no idea at all. Just wanted to show you that such questions can turn up in your examination, and if you're not sure about it, just leave it. Because right now I can see Haritanam, Manya got incorrect answers. So do not do any guesswork, please. Omar, Adnan, yes. Cool. Finally, this question, last question of the day. We've already revised this one. Iodine exchange. That is the Finkelstein reaction. Yes? That's the Finkelstein reaction. This reaction wherein you have a diazonium salt. This is known as a diazonium salt. And we will discuss this in detail when we revise the chapter of amines. We'll do amines very soon, and diazonium salts are formed in amines. Diazonium salts basically are N2 positives. Okay? So when you have an N2 positive, it's a very good leaving group. It leaves as nitrogen. So that can be substituted very easily. So when the N2 positives nitrogen leaves, you can substitute a chlorine over here, forming this particular compound. Such reactions are known as Sandmeyer reactions. When you use cuprous species, when you use copper chloride or copper with fluorine, something like that, okay? When you use compounds over here that contain copper in them and react them with diazonium salts, these type of reactions are called Sandmeyer reactions. The copper is important over here for Sandmeyer. Right? Then this reaction, let me revise this for you. If you have, say, an alkyl halide and you react it with sodium in the presence of a little bit of energy, this undergoes a free radical reaction mechanism, okay, and it produces a product where this thing is coupled with its own self. Yeah. Chlorine leaves from here, creates a free radical kind of thing, and that reacts with its own self, basically. Fine. So this type of a reaction is known as Wurtz coupling. Okay. This type of reaction is known as a Wurtz coupling reaction. Fine. Now, my dear friends, when you do the same type of reaction with a haloarine, this is a haloalkane. If you do the same type of reaction with haloarine, arenes are aromatic compounds. So if you have a benzene over here, let's say, you do the same reaction, same thing is going to happen. A coupling will happen over here. Nothing's different in the mechanism of the reaction. Both are free radical mechanisms. But since this reaction was done by a different scientist, this reaction is known as a Fittig reaction. Just a second. Wurtz reaction, Fittig reaction. Wurtz coupling, Fittig coupling. Same reaction essentially, but different substrates were used, and therefore different scientists worked on them, different names. So when you have just arenium, haloarenes combining and coupling with their own selves, this is your Fittig reaction. But when you have one haloalkane and one haloarene combining together with each other, then this is a Wurtz-Fittig reaction. All right. So options were given next to this question in JEE Main. So it was like A1, B2, C3, D4, A5, A4, B1, C3, something like that. Okay. Interestingly, only one of the options had D matched with 3. In JEE Main, when this question was asked, in the options, only one of the answer keys had D with 3. So even if you didn't know the first 3 reactions, you would still be able to get the correct answer if you knew that this is a Finkelstein reaction. Fine. JEE Main is extremely easy. Cool. Nice. So people, that concludes our session for today. All of these were JEE previous year questions with one very interesting JEE advanced previous year question as well. So the next session that we are going to have with each other is going to be on Friday, when we will discuss alcohols, phenols and ethers, and we'll revise that particular chapter. We'll revise the important reactions of that chapter, and next week again we'll do previous year questions of that chapter and then do aldehydes, ketones, etc. It'll go in sequence. Fine. Great. So thank you so much for joining in, people. I hope you enjoyed the session. I'm sure you've already subscribed to the channel. If you haven't done that, please do so, and make sure you hit that thumbs up button. That's pretty much it. Alrighty. Nice. Random bro, that's great, man. I hope this year you finally get to the college of your dreams. Haritanam was asking me about Paji. So Haritanam, the thing is that in Punjabi there are two words for brother. One is Veera and one is Paji. So some people say Veera, some people say Paji. Veera, Veere. Alright. So when you say Paji, it's nice. When you say Paji, it doesn't sound that nice. So yeah, a lot of people can't pronounce Paji because that has a Punjabi accent to it. So they call you Paji, and then Paji sounds very okay, fine. So you call me whatever you want. You call me bro, you call me sir, you call me Veere, you call me Paji. I'm fine with it. Strong and capable? Yes, I will do that, bro. मैं देख लूँगा आपका comment. Umar Adnan, that's great, man. Thank you so much. I do not know Tamil, bro. I am really sorry. The only languages I know are Hindi, English, Punjabi, just like 4 or 5 words of Kannada, and a little bit of Portuguese as well. Random bro is saying, can I skip my first attempt? Math is too bad. Don't do that, bro. Just do the best you can in your first attempt itself, and then do the second attempt as well, of course. But no matter what your condition is, do not skip the first attempt. Cool. Alright, people, I take your leave. I've been continuously speaking since 8 p.m. So I'm going to go home, rest, and then I'm going to see you guys on Friday at 6 p.m. For those of you who are watching my Vedantu JEE Hindi classes, I'm going to see you tomorrow at 8. Anyway, thank you so much for joining, people. Bye bye, good night, take care. All the best for your exams.